Hello and welcome once again to Aakash BYJU'S YouTube channel. My name is Atiullah and we are live once again with JEE Mission 2022. Alright guys, so before we start this session, just let me know if you can see me properly and if you can hear me clearly, and give me a thumbs up, give me a yes in the comment section so that we can start this session. Alright, so people joining in. Rishabh, hi, how are you? Muhammad Musharraf, how are you? Welcome guys, very warm welcome to this session. Hello Nishat, how is it going? Alright, perfect. So everyone can hear me see me clearly and hear me properly. So I guess we are all set to start this session. Okay, so in this session we are going to take up atoms and X-rays, and we are going to solve some important and previous year questions. And I have emphasized a lot on this, but pardon me, but I'm going to emphasize on it again that modern physics is your golden ticket to score well in physics. Okay. Now the only annoying thing I see in modern physics is there's a lot of calculation. Okay. That's something we cannot avoid. That's something even in competitive exams you get questions in which you have to do a little bit of calculation, and that can be a little annoying sometimes. But in this session I will try to give you a few tips. I'll try to give you a few techniques which will help you solve a problem in a way where calculation can be reduced. So watch out for that. And we are all set to start this session. Be ready with your notebook and pen because we are going to solve all the questions together. And here we go with this first question in this session. Alright, let's start with this question. Alright. So radiation coming from transitions n equal to 2 to n equal to 1 of hydrogen atoms fall on helium plus ions in n equal to 1 and n equal to 2 states. Okay. The possible transition of helium ions as they absorb energy from the radiation is. Alright guys, so here is the question for you. Read the question carefully and let me know how should we solve this question. First, I want to understand from you what is the approach that you would take, what is the key concept involved. Let's discuss that first. Remember, the idea here of the objective here is to discuss the concepts. We can solve problems, but we have to revise all our concepts. That's the objective. So quickly let me know how do you think we should proceed with this question, and then we are going to solve it. Alright. Alright, so we have answers coming in as already. So Rishabh is saying that the option is going to be C. But Rishabh, before we jump to the answer, my suggestion to you would be that, alright, now Rishabh has changed his answer. So my suggestion to all of you would be to give it a shot to solve this question, try to solve this, and then we should begin to discuss. But before that, obviously, we should look at what is the concept involved. Okay, so we should think about the concept involved over here. Alright, so now let's think about it. So if you attended my previous session, which was yesterday, or if you have attended any of our sessions in atoms, I told you something, okay? It is very good to remember the energy levels of hydrogen. Okay, what are the energy levels of hydrogen? Let's say this is n equal to 1, n equal to 2, 3, 4, 5. At least from n is equal to 1 to n is equal to 5, we should remember the energy levels. What are these energy levels? Minus 13.6 electron volt, and then we have minus 3.4 electron volt, and they have minus 1.5 electron volt. Then what is the next one? Then we have minus 0.85 electron volt. And for n is equal to 5, we have minus 0.55 electron volt. Okay, at least this is something we should remember, at least till n equal to 1 to n equal to 5, and this is going to make the question solving very easy. Now what has happened to the hydrogen atom? The hydrogen atom has gone from n is equal to 2 to n is equal to 1, which means what is the energy difference? The energy difference is going to be 13.6 minus 3.4, that is 10.2 electron volt. Do you agree? Is that correct? Okay. So the energy of the photon which is released due to the transition in the hydrogen atom from n is equal to 2 to n is equal to 1 is 10.2 electron volt. Is that right? Okay. Now just remember this 10.2 electron volt. Forget everything else. Now what do we have? We have this helium ion. Okay. We have this helium ion. Obviously it is going to have one electron in its outer orbit. and then this energy of 10.2 electron volt is incident. Okay, now here is a very important concept. When the transition, when energy is only going to be absorbed when the transition can happen, okay, which means that this 10.2 electron volt has to be equal to some transition corresponding to the helium atom. Is that right? Okay. Now, if we talk about the energy of the helium atom, there is a difference between there is a relationship between the energy of an atom and the energy of the hydrogen atom. What is that relationship? The energy of any atom can be given by Z square upon N square into minus 13.6 electron volt. Do you agree? Do you agree with this? Okay. So this tells me that this quantity over here is the energy of the hydrogen atom in the ground state, and this quantity over here is going to give me the energy of the hydrogen atom for different states. Okay. So I can say that the energy for any atom is going to be equal to Z square into the energy of the hydrogen atom. Do you agree with this? Let me know if you agree with this. Okay. So we can find the energy of any atom for the corresponding state by using E is equal to Z square into the energy of the hydrogen atom. Is that correct? Now we can also say that the change in energy, the energy of transition, what does delta E mean? Delta E means the energy of transition. Now the energy of transition will be equal to Z square into delta EH. Is that correct? Do we agree over here? Is that clear? Okay. Now what we have here is that this delta E is 10.2 electron volt. Do you agree? This is the energy of transition. For the helium ion, this is the energy of the transition. This is the energy absorbed by the helium ion so that our transition can happen. So delta E over here is 10.2 electron volt. Do you agree? Now from here what we can do is we can think that for the same transition in hydrogen atom, what will be the energy difference, or what will be the energy of transition? Okay, so what is happening is that the energy transition from, let's say, n is equal to 3 to n is equal to 1 in helium ion, what I'm doing is I'm comparing that to the energy of transition from the same n is equal to 3 to n equal to 1 in the hydrogen atom. Okay, because the energy values of hydrogen atom is something I know. Okay, it's something that I remember, so my calculation is going to become very, very easy. So see what I'm doing over here. Okay, so what is delta E? Delta E is the 10.2 electron volt. That is the energy of transition for the helium ion. This is equal to Z square. What is the atomic number of helium? It's 2. So this becomes 4 and multiplied by delta EH. So from here what do I get? I get delta EH is equal to 10.2 upon 4. And if I do this, what I'm going to get, this is 2, this is 5.1. So this is going to become 2.55 electron volt. Is that clear? Is this clear? Okay, up till this point. Now the magic is going to happen. Okay, now we are going to find out the transition just like that. Okay, but I want to understand from you that if you have understood this concept very well. Okay, so what did I do? I'm going to repeat myself. Okay, now the energy of any atom can be given by Z square into energy of the hydrogen atom. So the change in energy, the energy of transition for any atom should be equal to Z square into the change in transition for the hydrogen atom. Okay, so what I have done is that if the same state transition is happening between helium ion and hydrogen atom, then what I have figured out is that if 10.2 electron volt is the energy of transition for helium ion, then 2.55 electron volt will be the energy transition for the hydrogen atom for the same transition. From the same level to the same level in the hydrogen atom, 2.55 electron volt will be the energy of transition. Okay. Now we have all the values right in front of us. Now we can very quickly see that the difference of which two quantities is going to give me 2.55 electron volt. Now can you quickly tell me that what should be the transition in the hydrogen atom such that the energy of transition is 2.55 electron volt? Can you quickly tell me? Just look at the values. The values I've told you, remember the values, it's going to be much simpler. So look at the values and quickly tell me what should be, from which orbit to which orbit should the energy transition, should the transition take place. Can you quickly figure that out? Think about it. I'm going to wait for your answer. So you just have to check that the difference of which two energy levels is going to give us 2.55 electron volt. That's all we have to check. Quickly check and let me know. Absolutely, Sayyam is absolutely right. Absolutely right. So this is minus 3.4 electron volt and this is minus 0.85 electron volt. What is the difference? The difference is 2.55 electron volt, and hence we have the answer with us. So the transition for the helium ion is going to happen from n is equal to 2 to n is equal to 4. Is that correct? And this is going to be our right answer, from n is equal to 2 to n is equal to 4. Okay, so what I have done here is that the energy of transition for any atom, I can just relate that to the energy of transition of the hydrogen atom. So all I have to see is that in the hydrogen atom, what will be the corresponding energy change for the same change or for the same transition. Okay, and since I know the energy levels of hydrogen atom, my calculation is going to become very simple, and I bet you go and solve it without using or memorizing these energy values and see how difficult it is going to be. You are going to go crazy with calculation. Okay, so remembering just these energy levels for hydrogen atom is going to help you solve the questions in a much simpler way. Alright, agreed guys? Did you like the solution? Did you like this concept? Please put that over here. That gives me a lot of encouragement. And now let's go to the options. So option B is going to be the right option, and now we go to the next question. You ready guys? Let's get cracking with this one. Now the energy required to remove the electron from a singly ionized helium atom, okay, singly ionized helium atom is 2.2 times the energy required to remove an electron from helium atom. Okay, the total energy required to ionize the helium atom completely is, okay, so I want you to take a few seconds, get cracking with the question, think how we should proceed with it, think what is the concept involved, and then we are going to solve it. Think about it. Okay, so Rishabh is giving answers, but Rishabh, again I am saying the thing we are doing here is we are understanding the concepts, we are revising the concepts. So if you have solved it, but it will be great if you can share that what is the concept you have used, and that is going to help other people over here as well. Okay, so let me know how did you go about solving this question and what is the key concept that you used to solve this question. That is going to go a long way. Ajit is saying समझ में नहीं आया sir. Okay, question समझ में नहीं आया, कोई बात नहीं. Okay, Hyper Gaming, good evening, welcome. Alright, अगर question समझ में नहीं आया तो कोई बात नहीं, we'll go over it again, no worries. Okay, so what we have over here is okay, helium atom. Helium atom has how many electrons? Helium atom has 2 electrons. Do you agree? Of course you have to agree. There is no other way. You have to agree that helium has 2 electrons. Okay, now the energy when helium atom is in ground state, the energy required to take away 1 electron is called its ionization energy. Okay, so let's call it E1, the first ionization energy. Okay, so if we are taking the first electron out, it is called the first ionization energy. Now what will happen when we have taken out 1 electron? If we have taken out 1 electron, then this is going to become helium ion, and helium ion will thus have 1 remaining electron. Now if helium ion is in its ground state and we take away its electron, then the energy required to do that, it will be called the second ionization energy. Do you agree? Do you understand this? So we are taking away 1 electron, it's called the first ionization energy. We are taking away the second electron, it is called the second ionization energy. And the relationship given here is that the second ionization energy is 2.2 times the first ionization energy. That's obvious, okay, because now it has become helium plus. Okay, so this was helium and there were 2 electrons, now it has become helium plus. So obviously the energy required to take out the second electron is going to be larger, right? So E2, the energy required to take out the second electron is 2.2 times the energy required to take out the first electron. Now the question is, how much energy would be required to take out both the electrons. Okay, so we'll have to take out the first electron first, and then we'll have to take out the second electron. So we have to figure out what will be the total energy required to take away both the electrons from the helium atom. Okay, and this relationship is given. So this is the question. I want you to give it another shot and see if you can get this right. Okay. Known unknown is asking, sir, please answer one query. अरे बताओ तो भाई query क्या है? Let me know what is your query. If it is related to our session, to our concepts, then definitely. Alright, so ask away. So we are live, guys, so make use of the fact that we are live. If you have any confusion, any doubts, you want to ask related to this session, if something you have not understood, something you want to understand, ask away, don't be shy, and I'm going to answer all your queries. Okay, it's just that it has to be related to this topic. Alright, any luck, guys? Alright, let's look at this. Now first let's talk about E2. Because this is helium plus ion, Bohr's model would be applicable. Do you remember Bohr's model? I'm sorry, I've got the spelling wrong. So Bohr's model is applicable for isoelectronic species. Isoelectronic species means they can only have one electron. Isoelectronic species. So hydrogen atom is an isoelectronic species. Helium plus, okay, helium has 2 electrons, helium plus has 1 electron, so it is an isoelectronic species. Lithium 2 plus is an isoelectronic species. So for all these isoelectronic species, Bohr's model is going to be valid. Okay, now it is in its ground state, okay. Now the energy required to take out the electron, how much is that going to be? Okay, let's talk about the hydrogen atom. For reference, let's talk about the hydrogen atom. So let's say hydrogen atom has 1 electron. So in the ground state, the energy of this atom is going to be minus 13.6 electron volt. Now when we are saying that we have to take this electron away, which means that there should be no interaction between the hydrogen atom and electron, which means we are separating them to a very far distance, which means their energy is going to become 0. So how much energy will we have to provide? We'll have to provide 13.6 electron volt. Okay, is that clear? So whatever is the energy in the ground state, the same quantity in positive, the modulus of that quantity we have to provide to ionize the atom. Do you agree with this? Okay. Now what we have to understand here is that the energy for any atom, like we discussed, is Z square upon N square into minus 13.6 electron volt. Do you agree? The energy for any atom will be given by this. And what are we talking about? We are talking about the ground state. Okay. So N is going to become 1. Is that clear? So this energy is going to become, let me write it over here, this energy is going to become Z square into 13.6 electron volt. And what is Z? For the helium atom, the Z value of Z is 2. So this is going to become E into minus 13.6 electron volt. So energy of the helium ion in the ground state is 4 into minus 13.6 electron volt. If we have to ionize this atom, then how much energy we have to provide? We'll have to provide the modulus of this energy. Is that correct? Is that clear? Any problem over here? I hope this is clear. Okay, so I'm going to draw this again, no worries. So we have helium, there are 2 electrons, the first one goes away, so this is called E1, and then we have helium plus ion, and then this is the electron, and then okay, this electron is gone. Let's talk about this electron. Now when this electron goes away, this is E2. So what we have figured out is that the energy of the helium ion in the ground state is 4 into minus 13.6 electron volt, which means that the energy I will have to supply, and I'm calling it the second ionization energy because this is the second electron we are taking out. So E2 is going to be equal to 4 into 13.6 electron volt. Do you agree? Any problem? I hope this is clear. Okay. Now what is also given to me is that E2 is 2.2 times E1. Do you agree? So from here what can I say? From here I can say that E1 is equal to E2 divided by 2.2. So from here I can find out what is E1 as well. So E1 is going to be 4 into 13.6 electron volt divided by 2.2. So what I have done is I have found out E2 and I have found out E1 as well. And what will be the total ionization energy? What will be the total ionization energy? I'm going to write it over here. The total ionization energy is going to be very simple. It's going to be E1 plus E2. So we take the first electron out, E1 energy is supplied. We take the second electron out, we supply E2 amount of energy. So I found E1, I found E2. Now it's just calculation that is remaining, and this calculation is not very tedious, I get. This is a fairly straightforward calculation. So if you do this calculation, you are going to get the answer as 79 electron volt. And that is going to be our answer. Is that clear? Okay, any confusion regarding this question, anything you did not understand, anything you want to ask, you can surely ask away. Yes, Karthik, the answer is going to be 79 electron volt. You are absolutely right. Sayam, yes, 79 electron volt was the correct answer. Absolutely. Alright, so I hope this is clear and we have understood that what is ionization energy, and we have solved this question. Alright, perfect. So option B is going to be our correct option. And then let's go to the next question. Alright, let's solve this question. We'll have, looking at the options. So options are A, B, D, B, D, C, D, A, C, D. So which means probably we'll have to look at each and every option. Okay, not a problem. So we have a particle called muon. Okay, we have a particle called muon, and it is negatively charged and it has the same charge as the electron, and the mass of the muon is 200 times the mass of the electron. Okay, now Me over here is the mass of the electron and E is the electronic charge. Is that clear? So what particle are we talking about? We are talking about a particle called muon, which has the same charge as the electron. Muon is also negative, electron is also negative, the magnitude of charge is also same. Okay, the mass of the particle muon is 200 times the mass of the electron. Okay, now we have to identify what are the correct statements. So what are we looking at? We are looking at radius of the muonic orbit is 200 times smaller than the radius of the electron. Okay, so in one situation where there is an electron which is revolving, and then in another situation when there is this particle muon revolving, then we have to compare their radius. Then we have to compare their speed. The speed of muon in the nth orbit is 1 upon 200 times that of the electron in the nth orbit. So we have to compare the speed, we have to compare the ionization energy, and we have to compare the momentum as well. Is that clear? Okay, so Hyper Gaming is saying bulky question. See, the question is not bulky, question is only 2 lines and it's a very straightforward question. The options you see, you'll have to analyze each and every option. Okay, so don't be apprehensive, or don't before attempting the question, don't get scared of the question. Okay, go through the question, go through the options, and then attempt, and then understand ki, okay, this is going to be the right approach, and then you decide that if it is a difficult question or not. Bulky is not a problem, difficult or not difficult, that is a problem. Okay, so and I'm going to show you that we can solve this question very easily. Okay, that's what I'm going to show you. Okay, so if the question is clear, let's try to solve this question. Okay, now compare the two situations. So all we have to do is we have to compare the two situations. What is the situation? Let's say in the hydrogen atom there is one proton and there is one electron. This is situation number 1. In situation number 2, we have one proton, and instead of the electron we have a muon. This is the situation. Okay, And the only difference is that muon has greater mass. Mass of muon is 200 times the mass of the electron. Okay. Now remember, how do we derive radius? How did we derive speed? How do we derive energy in Bohr's model? That is a derivation that we have to know. Okay. So nothing escaping it. You cannot just get away by memorizing the results. You have to know the derivation. Okay. And I'm going to derive it in front of you, and you are going to see that it's a 2-line step. That's it. Deriving all the things in Bohr's model is a 2-line step, and I'm going to exhibit that. And if you have to remember that, or you have to practice that, you have to be well versed with that. Okay. That's something we have to do, because they can change the system. They can change the system anytime. They can even change the nature of force anytime. Okay. So let's talk about this. Now we are talking about the hydrogen atom. Plain and simple, we are talking about the hydrogen atom. Okay. So the force, the centripetal force, what is the centripetal force? The centripetal force is this. The centripetal force is the electrostatic force. Is that correct? So the centripetal force is electrostatic force. So this is going to be 1 upon 4 pi epsilon naught E square, E into E, Q1 Q2 divided by R square. This has to be equal to mv square upon R. Do you agree? Okay, so this is the equation for circular motion. So what are we going to get? This R and this R is going to go away. Okay, and what we have here is, let me write it down over here. So E square divided by 4 pi epsilon naught is equal to mv square R. Is that correct? Okay, we have found this relationship. But what I'm going to do over here is, I'm going to multiply both sides by R. So this becomes R square. And then I'm going to multiply both sides by m, so that it becomes m square. Okay. Now what we have on the right hand side is mvr square. And do we know what is mvr? What is Bohr's quantization rule? Mvr is the angular momentum, and this can be equal to nh upon 2 pi. Do you agree? Any problem over here? Okay. So all we have to do is, we have to square mvr. Okay, we have to square mvr. So I'm going to write it in the next page, or probably we can write it over here, not a problem at all. So this becomes m e square r upon 4 pi epsilon naught is equal to, this is going to become n square h square divided by 4 pi square. So 4 pi from here and 4 pi from here is gone, and what we have is r is equal to n square h square upon e square epsilon naught divided by m. Is that clear? Any confusion over here? So look, just in 2 steps, look at this, just in 2 steps I have derived the radius. Okay, it's not a very big derivation. Okay, if you remember this, just 2 steps. In 2 steps I have I have found out what is the radius. Is that clear? Okay, so the radius is n square h square divided by e square epsilon naught m. Let's write this down. We have derived this. We have worked hard to derive this. Not really worked very hard, right? Just 2 steps. So what was that? N square h square upon e square epsilon naught m. N square h square epsilon naught, and then we had e square, and then we had m, right? So this is the relationship, this is the radius. Now you compare this, for which particle we have calculated this? We have calculated this for the electron. Okay, we have calculated it for electron. Now you compare between electron and muon, what are the things which are going to be constant? Okay, n is going to be constant. Okay, because we are going to compare the same n in both sides. Okay, we are going to compare the same n for the electron and for muon. So n is the same, h is a constant, epsilon naught is a constant. Okay, the charge of muon is also the same, so e square is also constant. So all these terms are constant between the electron and the muon. What is the thing which is not constant? Mass is the thing which is not constant. So what we see here is that the radius is proportional to the inverse of m. Radius is inversely proportional to the mass. Is that correct? Now if we know radius is inversely proportional to the mass, now muon has mass which is greater than the mass of electron by 200 times. So its radius is going to be 200 times lesser. Do you agree? So option A is going to be absolutely correct, because we have figured this out. The radius is inversely proportional to the mass. So for the muon, the mass is 200 times greater, so the radius is going to be 200 times smaller. Do you agree? Yes, Karthik, A is absolutely correct. But we'll have to look at each and every option, because that is the nature of the options given to us. We'll have to look at each and every option. So option A is certainly correct. Any confusion over here? Okay. Now let's talk about option B. What is option B talking about? Option B is talking about the speed. Okay. So we have to find a relationship between the speed and the mass. So what do we have? We have mvr is equal to nh by 2 pi. Do you agree? So from here what I can say is that m into v, so from here I can say that v is equal to nh upon 2 pi and then m into r. Is that correct? Any problem over here? Okay, so v is going to become, now what are the things which are constant? These are the things which is constant. So v is inversely proportional to mass and v is inversely proportional to radius. Okay, but radius we are seeing is inversely proportional to mass. Over here radius is inversely proportional to mass. So I can write v is proportional to 1 by m, and for radius I can write 1 upon m. Is that correct? So v is inversely proportional to m and then inversely proportional to r. So for r I can replace it by 1 by m. So this m is this m is gone, which means v does not depend on m. Can you see that? Okay, so v does not depend on m, and if v does not depend on m, then its speed is going to be the same as that of the electron. So option B is not going to be the correct option. Is that correct? Any problem over here? Alright, now let's go and look at option C. We have to talk about the ionization energy of muonic atom, 200 times more than that of the hydrogen atom. Okay, so we have to look at ionization energy. What is ionization energy? Ionization energy is just the negative of the total energy. Do you agree? Ionization energy is just the negative of the total energy. Now let's talk about the potential energy. What is the potential energy? Potential energy is going to be 1 upon 4 pi epsilon naught into E square divided by R. Is that correct? And there's going to be a negative sign because electron is negatively charged. Do you agree? So that is going to be the energy. Is that correct? That is going to be the energy. Okay. Now we know that is the potential energy, and we know the total energy is half that of potential energy. So this is going to be minus 1 upon 8 pi epsilon naught E square divided by R. Do you agree? So this is the total energy. So the ionization energy is going to become, the positive of this quantity. So it is going to be, come on, 1 upon 8 pi epsilon naught E square divided by R. Correct? Any problem? Okay, so from here what do we get? We get that E ionization is inversely proportional to R and R is inversely proportional to M. So E ionization is going to be proportional to M. Can you see? Okay, all these are constant quantities. E of ionization is inversely proportional to R and R is inversely proportional to M. So E of ionization is going to be proportional to M. Is that clear? Pretty straightforward. Okay, so we have figured that out. So option C is also going to be the correct option because it is given that ionization energy of muonic atom is 200 times that of the hydrogen atom. Correct? So we have solved option C also. Now let's look at option D. Okay, option D is left. We have to talk about the momentum. Okay, so I'm going to rub this off for clarity. Let me rub this off. Okay, now let's talk about momentum. So momentum is simply m into v. Correct? Now momentum depends on mass. It is proportional to mass, and the speed is not proportional to mass. The speed is independent of mass. So we can simply say that the momentum is going to be proportional to mass. Is that correct? Other things we know that is going to be the same. So the momentum is also going to be 200 times than that of the electron. So option A, C and D are going to be the correct options, which means A, C, D are our correct options. And if we look at the options which are given in the question, then option D would be correct. A, C, D are correct. Is that clear? Okay, perfect. Yes guys, you're absolutely right. Sayam, you're right. Karthik, you're right. Hypergaming, you're right. Not completely. Hypergaming, A, C, D are all the correct options as per the question, and the options that are given to us, then looking at option D, that is going to be the correct option. Okay, now what did we learn over here? What is the key takeaway? Can any one of you tell me what is the key takeaway from this question? What knowledge did we have helped us solve this question? Anyone? What is the key takeaway from this question? Yes, Rishabh, option D is going to be the correct option. Absolutely right. But what I wanted to understand from you is that, did you understand what is the key takeaway from this question? What is it that you have to keep in mind? Okay, and I've said this before and saying this again. You have to be able to derive. Okay, and the derivation is not memorization. It's very straightforward. You have the centripetal force equal to mv square by r, and there is Bohr's angular momentum quantization rule. That's it. Those are the two equations, and you can use that to solve all of them. So derivation, being able to derive Bohr's model, is very important, because you know that it cannot stick to hydrogen atom. The nature of force can change. They can talk about any hypothetical situation, so we don't want to be dead ducks there. We have to be able to navigate through difficult circumstances. Okay, so that is why derivation is very important. Alright, Karthik, see, you don't have to remember the derivation, don't memorize the derivation, but you should be you should be in a position to understand that how is this derived. What are the key principles? And that's what I said. I do not remember any of the derivations. I do not remember the derivations. What I remembered about Bohr's model is there are only two things. One, it is going in a circular orbit, so there is centripetal force. Centripetal force will be equal to mv square by r. And the second thing is Bohr's angular momentum quantization rule, that mvr is going to be equal to nh by 2 pi. I have memorized nothing else. Those are the two principles. I use those two principles to derive it. So you don't have to memorize derivation, but you have to understand that how it is derived. What are the key concepts that are used, or what are the key conditions that are used? What are the key assumptions that are used to derive it? Okay, that's what we need to know, and that is very, very important. Alright, perfect. So now we go to the next question, and here is the next question for you. A neutron moving with a speed v makes a head-on collision with stationary hydrogen atom in ground state. The minimum kinetic energy of the neutron for which inelastic collision will take place is. That's the question, and before we proceed to the solution, I want to understand from you, how should we proceed? Okay, what is the key concept involved? So this has to do a little bit with collision as well. So good revision of collision also. Think about it. So we have this neutron, it is moving with a speed v, and then we have this hydrogen atom which is stationary. So what is happening after that? When they collide, what is going to happen? It is given in the question that it is a perfectly inelastic collision. Inelastic collision meaning that they are going to move together. Okay, and if they're going to move together, let's say we assume that the velocity becomes v prime, the common velocity becomes v prime. Now we know that neutron and hydrogen atom, okay, they have almost the same mass. They don't have equal mass, they are not perfectly equal, but they have almost the same mass. So what I'm going to do is I'm going to treat them as particles of equal mass. Okay, so what is the initial momentum? The initial momentum is mv, and the final momentum is 2mv prime. Okay, I hope this doesn't need any explanation. That's pretty self-explanatory. So v prime becomes v upon 2. Okay, now what is the loss in kinetic energy? What is the loss in kinetic energy? The loss in kinetic energy is half mv square. That was the initial kinetic energy, minus, what is the final kinetic energy? The final kinetic energy is half into 2m into v prime. What is v prime? V by 2. So v by 2 square, which means v square upon 4. Is that correct? Okay. So this 2 and this 2 is gone. So we have 1 upon 4 mv square. So what does it tell me? It tells me that the loss in kinetic energy is equal to half of half mv square. Do you understand this? And what was half mv square? Half mv square was the kinetic energy. Is that correct? Half mv square was the kinetic energy of the neutron, and the loss in kinetic energy is half of that value. Is that correct? Any problem there? Okay, so what we have figured out is that the loss in kinetic energy is half of the kinetic energy of the neutron. Correct. So what we need to find out is kinetic energy of the neutron. So that is 2 into loss in kinetic energy. Is that clear? Perfect. Now the question is that this loss in kinetic energy, where is this going to go? Where is this going to be utilized? So we have the hydrogen atom. This is minus 13.6 electron volt. N is equal to 2 is minus 10.4 electron volt. N is equal to 3 is how much? It is minus 1.4. I'm sorry, this is 3.4. My bad. Minus 3.4 electron volt. N equal to 3 is minus 1.5 electron volt, and so on. Okay. Now this energy that is being lost is going to increase the energy of the hydrogen atom. Okay. And what is the minimum increase in hydrogen atom possible? Now remember, an atom is only going to increase, is going to absorb energy if a transition is possible. Okay, remember this, very important. This is very important. An atom can only absorb energy if a transition corresponding to that energy is possible. Okay, so what is the minimum energy of transition? So it can go from the ground state to n is equal to 2. Okay, the hydrogen atom is the ground state, so the minimum energy it has to take to go to n is equal to 2. And how much is that energy? That energy is 10.2 electron volt. Do you agree? This atom is only going to absorb energy if there is some transition. And transition, the minimum amount of energy required to have a transition is when the transition is going to happen from n is equal to 1 to n is equal to 2. So the energy of transition is going to be how much? The energy of transition is going to be 10.2 electron volt. And this is the energy hydrogen atom has to absorb. This is the minimum amount of energy that the hydrogen atom has to absorb. Is that correct? Okay. So what was the loss in energy? Loss in energy was equal to 2 into kinetic energy of the neutron. And what is the minimum loss in energy? The minimum loss in energy is 10.2 electron volt. I'm sorry, this is K by 2. This is K by 2. So the minimum loss in energy is 10.2 electron volt. This is equal to K upon 10. So the minimum value of kinetic energy of the neutron should be 20.4 electron volt. Is that clear? Okay. Tricero is saying, I have a doubt, sir. Bilkul pucho yaar. What's your doubt? Let me know. Alright. Now I want to know from you guys. Did you get this? Did you understand what is happening in this question? And there are two very important points. There are two very important takeaways from this question. Can you tell me what are those two important takeaways from this question? Can you quickly tell me? Alright, the number one thing is that if you remember these values, it is going to be very easy. Okay, if you remember the energy levels of hydrogen atom, different states, then this is going to be very helpful in your calculation. And the second thing is, an atom is only going to absorb energy if a transition is possible. If for that energy transition is not possible, it is not going to absorb that energy. Alright. So that's done. So that's our answer, 20.4 electron volt. So option A is going to be our right option. And now we move to the next question. Okay, what's the question? A diatomic molecule is made of two masses m1 and m2 which are separated by a distance r. If we calculate its rotational energy by applying Bohr's rule of angular momentum quantization, its energy will be given by. Okay. Is the question clear? And before we proceed, I want to know from you, how should we go about it? Okay. So we have two particles. We have a diatomic molecule. Okay. So this is one atom. This is the other atom. The distance between them is r. Okay. And it is going to rotate. Okay. It is going to rotate. And we have to find out what will be its energy of rotation, what will be the kinetic energy of rotation, and it is given to us that Bohr's rule of angular momentum quantization is applicable, so we can apply that. Okay, the angular momentum of the system can only be integral multiple of h by 2 pi. Is that correct? Okay, so first we are talking about the rotational kinetic energy, so we'll have to involve rotational kinetic energy. Second, we are talking about angular momentum, so we'll have to involve angular momentum as well. Okay, so how I'm going to do it is I'm going to find out what is the moment of inertia about the center of mass, and I can say that the kinetic energy is half into ICM omega square. Can I do that? Now they are going to rotate about the center of mass. Let's say this is the center of mass. The distance of particle 1 from the center of mass is r1. The distance of particle 2 from the center of mass is r2. Okay. Let's say this is the situation. Okay. And it is going to rotate. Now if it is going to rotate, they are always going to be diametrically opposite. And if they are always going to be diametrically opposite, then the angular velocity of both m1 and m2 is going to be the same. Let's assume that is omega. Okay. So the kinetic energy of this system is going to be half into ICM into omega square. Is that correct? That is the kinetic energy of rotation. What about the angular momentum? The angular momentum is going to be ICM into omega. Do you agree? Okay, the angular momentum is going to be ICM into omega. Is that clear? Okay, so let's try to do this. First of all, let's find out what is ICM. What is the moment of inertia about the center of mass? Okay, so this is the axis. So moment of inertia of particle 1 is going to be m1 r1 square, and moment of inertia of particle 2 is going to be m2 r2 square. So that is the moment of inertia of the system about the center of mass. Correct? Okay. Now let's look at these two relationships. Angular momentum is equal to ICM into omega, and this is going to be equal to NH divided by 2 pi. Do you agree? Okay. So what I can do over here is that I can use this equation. So this becomes L is equal to ICM, which is m1 r1 square plus m2 r2 square. And what do we have? We have omega. This is going to be the angular momentum, and this has to be equal to NH upon 2 pi. Is that correct? So from here, what do we get? From here we get omega is equal to NH divided by 2 pi into m1 r1 square plus m2 r2 square. Is that correct? Any problem over here? So what we have done is we have found out what is omega. Okay. Now this omega we can substitute over here and find out what is the rotational kinetic energy. So let's do that. So the kinetic energy is going to become half into ICM. What is ICM? m1 r1 square plus m2 r2 square into omega square. Now what is omega over here? Omega over here is NH upon 2 pi divided by m1 r1 square. So this is going to become NH upon 2 pi, then m1 r1 square plus m2 r2 square, and the square of this. Is that correct? So this is how I have figured out what is the kinetic energy. Is there any problem? Okay, I hope this is clear. So this 1 m1 r1 square plus m2 r2 square and this 1 m1 r1 square plus m2 r2 square, that is going to go away. So this is going to go away. So what do we get? We get kinetic energy is equal to half n square h square divided by 4 pi square and then divided by m1 r1 square plus m2 r2 square. Is that correct? Okay, now let's look at this. What is the relationship between r1, r2 and r? So this total distance is r. Let's say this is m1, let's say this is m2, this is r1 and this is r2. Okay, now what is the relationship between r1, r2 and r? Can someone tell me? This r1 is the distance of the center of mass from particle 1. This is going to be equal to m2 r divided by m1 plus m2. Do you remember this? Okay, so the distance of the center of mass from the first particle will be equal to m2r into m1 plus m2. Okay, so the center of mass divides the line joining the two particles in inverse ratio of their masses. Okay, similarly, what are we going to get? We are going to get r2 as m1r divided by m1 plus m2. Now all we have to do is do the substitution in this equation. So kinetic energy is going to become n square h square upon 8 pi square, and then in the denominator we are going to have m1 and then r1 square is going to be m2r by m1 plus m2, or let's do it in the next slide. Alright, I'm going to do that in the next slide. So kinetic energy is going to be n square h square upon 8 pi square, and then we have m1 into r1 square. What is r1? r1 is m2r upon m1 plus m2 square, and then we have m2 into r2 square. Okay, this is all in the denominator. m2 into r2 square, and what is r2? r2 is m1r upon m1 plus m2 and the square of that. Okay, so let's calculate this. This becomes n square h square upon 8 pi square. Then in the denominator we have m1 plus m2 square, so this m1 plus m2 square is going to go upstairs, and then if we take m1 m2r as common, we are going to be left with m1 plus m2. So this m1 plus m2 and this m1 plus m2 is gone, and finally we are left with n square h square upon 8 pi square, and then we have m1 plus m2 over here, and then we have m1 m2r over here. Is that right? Okay, so that is going to be our answer. Now in the option, none of the options are matching with the answer, so we will go for the closest option. Okay, we are going to go for the closest option. Unfortunately, none of the options given is exactly right, but it's almost right, so we are going to go for the closest possible option. Okay, so the closest possible option is option A, so we are going to go with that. Is that clear? So as I said, you can be given very different kinds of situations, very different kind of systems, but the concepts are still going to be the same. Okay, Bohr's quantization rule, the concept is the same, that the angular momentum is going to be nh upon 2 pi. Now the ways of calculating angular momentum can be different for different systems, but the concept is still going to be the same. So we use the same concept and we solve this question as well. Is that right? Hypergaming is saying, sir, this question has so many substitution. Nice question. Yes, it does have a lot of substitutions, but I solved it in a more regular way. I could have got a little smart and I could have solved it in an easier way also. There you wouldn't have to do a lot of substitution, and you can also do the same. Okay, you can revisit this question and see how you can reduce your calculation. Okay, that is going to help you. Alright, now let's go to the next problem. In the Bohr's model, an electron moves in a circular orbit around the proton, right? Considering the orbit of electron to be circular current loop, that's legit, isn't it? So electron is moving in a circular radius, electron is moving in a circular path, and electron is a moving charge, and moving charge is electric current. So this is quite legit. And if there is electric current, there is going to be a magnetic moment. So the magnetic moment of the hydrogen atom when the electron is in the nth excited state is, and these are your options. Okay, so think about the question. and let me know what is the key concept involved. So this electron is moving in a radius of, let's say, r, and because of this motion of the electron, this can be considered as a circular loop in which current is flowing. Is that correct? Okay, so we have to find out what is the magnetic moment. So the first thing obviously to understand here is what is magnetic moment. What is magnetic moment? So magnetic moment is I into A. Do you agree? The magnitude of magnetic moment is I into A. So I'm going to write it as I into pi r square. Okay, or I'm going to write it over here. So if it is going in a radius of r, this current carrying loop has a radius r, which means that the area enclosed in that loop is pi r square. So magnetic moment is going to be I into pi r square. Is that correct? Any problem? Okay, now we have to figure out what is I. What is I? Let's think about that. So first thing first, so what is the charge that is flowing? The charge that is flowing is E, and how much time is it completing one loop? In how much time is it completing one loop? So let's pick up any point. So through this point, how much charge is flowing in how much time? So charge equal to the electronic charge is flowing in one time period. Is that correct? So I'm going to write charge divided by time. And what is this time? This time is going to be one time period. And what is one time period? It is 2 pi r divided by V. Do you agree? The time it takes to complete a circle is going to be 2 pi r, the circumference, divided by its speed V, and then we have to multiply it by pi r square. So this pi and this pi is gone, this r and this r is gone. So mu will come out to be E divided by 2 into V into R. Is that correct? Any problem? Okay, so we have calculated what is the magnetic moment in terms of V and R, but that cannot be the final answer. Okay, so we have to find out another relationship for VR. And what is that relationship? Obviously, Bohr's quantization rule is going to be true over here. So the angular momentum mvr is going to be equal to nh by 2 pi. Is that correct? So from here what we can take is, we can take this Vr and substitute it. So this is going to become mu is equal to E divided by 2, and in place of Vr I am going to write nh divided by m into 2 pi. Okay, so I can write this as mu is equal to E upon 2m and then nh upon 2 pi, and that is going to be the magnetic moment. Is that clear? Okay, so this is another concept which is asked in this question, but we don't have to remember it. Okay, that's something we have not studied in Bohr's model. That's not probably related to Bohr's model also, but there's something, a question can be framed where you have to use the concepts of Bohr's model. Okay, so you have to be ready with that. If you are well versed with the concepts of Bohr's model, you can apply it in a strange situation also. Okay, so that's where your strength should lie, and that's where you'll be able to solve the best kind of questions, and you'll be able to score the best kind of marks. Okay, there should be readiness for some element of surprise. All right, so this is done, and option C is going to be our correct option. So now let's look at another problem. Okay, now this problem is related to X-ray diffraction, and X-ray diffraction is something we have to study in X-ray. So do pay attention. Very simple, these things are very simple, and these are going to fetch you marks. And also I'm going to tell you about a few shortcuts also. Okay, big question, let me read it out for you. Questions are based on the following paragraph. So wave property of electron implies that they will show diffraction effects. Wave property of electrons, we know that particles also have wave properties, so electrons can also exhibit wave properties. So Davison and German demonstrated, that is a very famous experiment, Davison and German experiment, demonstrated that by this diffraction electrons from crystals, okay, they showed that electrons can be diffracted from crystals. Now the law governing the diffraction from crystal is obtained by requiring that electron waves are reflected from the planes of the atoms in a crystal and interfere constructively. Electrons accelerated by potential difference V are diffracted from a crystal. Now D is given to you as 1 angstrom. What is D? D is the distance between two layers of atoms. Okay. I is 30 degree. This electron beam, the angle of incidence of the electron beam is 30 degree. So we have to find out what should be the value of V. Is that correct? Okay. So I'm going to pause over here for a few seconds. Read this question properly so that you understand it well, and then we are going to talk about the solution. But go through this question well and make sure that you understand the question first. Okay. I'm going to give you some time for that. Alright, I hope this is clear. The question is clear. So let's go for the solution. Let's see how to think about it. Okay. Now this is one electron beam. This is one electron beam, and we'll have to treat electron beam as a wave. So this is one wave coming in, gets reflected at this point, and then there's the outgoing beam. And then this is the second beam. Now you can notice that both these beams or both these waves are traveling unequal paths. There's a path difference between the two. And if there is path difference between the two, there is going to be a phase difference between the two. And if there is a phase difference between the two, then obviously they are going to interfere. And we can show that for certain angles and for certain velocities of the electrons, constructive interference can take place. Is that correct? Alright, so let's think about it. Let's find out what is the path difference. Now both these beams are coming from a very distant point. So we can assume that they are coming from the same point. They are parallel beams. Can you see that? They are parallel beams. So we can assume that they are coming from a same very far off point. Now what we do is we drop a perpendicular over here. So the second beam, it is traveling some extra distance. Can you see that it is traveling this much of extra distance? Let me change my pen and show it to you. This is the extra distance traveled by the second wave. Do you agree? Okay. For its inward journey, and for its outward journey, this is the extra distance traveled by the second wave. Do you agree? Okay. So this is the path difference. This is the path difference. Now let's think about these angles. So if this angle is I, this angle is also going to be I, and this angle over here is going to be, let me very carefully write this. This is 90 minus I. Do you agree? And I want you to look at this triangle. Okay, I want you to look at this triangle. This distance over here is D, and this is a right angle triangle, and this angle over here is 90 minus I, which means I'm sorry, that angle is not going to be 90 minus I. This angle is going to be 90 minus I. This angle over here is going to be 90 minus I. Can you see that? Okay. Now if you look at this triangle, then if we have to get this distance over here, this is going to be how much? This is going to be D sine 90 minus I. This distance over here is going to be D sine 90 minus I. Is that correct? Any problem? So I'm going to blow up this triangle and show it to you. So this is the right angle triangle, this is the distance D, and this is the angle 90 minus I, and this is the distance we need to figure out. That's it. That's the blue triangle that I showed you. So this is obviously going to be how much? This is going to be D sine 90 minus I. Okay. So how much is that distance? That distance is D cos 90 I. D sine 90 minus I is going to be how much? D cos I. Okay. And it is this distance over here. Let me show that to you with another color so that there is no confusion. This distance over here and this distance over here are the same, and that total distance is the path difference. So what is the total path difference? The total path difference is 2d cos I. Okay, and if constructive interference has to take place, then this path difference has to be equal to what? It has to be equal to n lambda. And what is lambda over here? Lambda is the wavelength. And for a particle, how do we define the wavelength? We define it by the de Broglie wavelength. Do you remember? De Broglie wavelength. So what is this lambda? This lambda is the de Broglie wavelength. Is that correct? Is the X-ray diffraction clear? Any problem over here? This is also called Bragg's law. Okay, so is the X-ray diffraction clear? Now if this is clear, then all we have to do is we have to do a simple calculation. So this is 2d cos I and this is equal to n lambda. Okay. Now lambda, this is something we should remember. We should remember the accelerating voltage, the relationship between the accelerating voltage of the electron and its de Broglie wavelength. That is something which can be used as a standard result. So that is 12.3 divided by root V angstrom. Otherwise you'll have to do a lot of calculation. Okay, but this is something that we should remember. The de Broglie wavelength of an electron is given by 12.3 divided by root V, where V is going to be in volts angstrom. Is that correct? Okay, all we have to do is do the substitution. So this is going to become 2. The value of D is given to us as 1 angstrom. And then cos I. What is I? I is 30 degree. So cos I is going to be root 3 by 2. And then this is going to be in angstrom. Then we have n multiplied by lambda, which is 12.3 divided by root V angstrom. Right, so on both sides we have angstrom, so we don't have to worry about the unit. This 2 and this 2 is gone. So basically what do we get? We get V is equal to n square 12.3 square divided by 3. Is that correct? And that is the relationship we get. If you don't use this relationship, if you don't remember it, it is going to be very tedious calculation, very tedious calculation. Okay, so this is something that we can remember and sort of in a standard result. Okay, because this is going to come in many places. So V is going to come out to be, if you calculate 12.3 square divided by 3, it will roughly come out to be 50 volt. So this is going to be n square into 50 volt. Is that correct? Now we can change the value of n and we can find out what are the voltages through which they can be accelerated. So one answer is right in front of you. If you take n is equal to 1, then V is going to come out to be 50 volt. Okay, but if you V is equal to n square into 50 volt. But if you make n is equal to 2, it is going to be 4 into 50, which is 200 volt. So you are going to see that whatever value of n you are taking, you will never find these values. Okay, you can check for that. You are not going to find these values. So corresponding to n is equal to 1, V is equal to 50 volt is certainly going to be the right answer. And also there is only one option correct, so you don't have to check that also. You can directly say that B 50 volt is going to be our answer. Is that right? Any confusion here? So I hope you have learned Bragg's law. Okay, very simple concept, but don't ignore X-rays, study X-rays also, because it will be a gift. It will give a gift from the examiner to you. If you know this concept, you will know this. You can solve this very easily. Alright folks, so that is it for this session. I hope this session was helpful for you. And next week, I'm going to see you in another session. We're going to take up another topic and we're going to do a thorough revision of that. So till then, keep practicing, keep getting better and have fun with learning. See you very soon.